I'd like to chat with you real quick about how to deal with systems of equations. This is something we chatted about once before, but it might be helpful to sort of see how I think through this. So let me just talk through a problem real quick with you. Let's suppose I had a problem with five variables. So something like 2x1 plus 4x2 plus, let's say, no x3s, plus 6x4s plus no x5s equals 4, no x1s, no x2s. We'll make this a little easy on me. Let's take an x3, 2x4s, no x5s equals 3. Let's take an x1, 2x2s, an x3, 5 x4s, an x5 equals 9. Well, if you reduced that, it would come out to, let's see, x1, and I'll just trust that you can, say, rescale these things appropriately. 2 x2 plus out to 3x3 equals 2. And then, let's see, the next equation would be x3 plus 2x4. I guess this should be an x4 equals 3. And then I'd have, let's see, so I scaled the first line by a half, I left the second line unchanged. If I subtracted this first line and this second line actually from the third line, I should come out with something that actually has no x1s, no x2s, no x3s, no x4s, and one x5. So we've got x5 equals 2. So if you did this in terms of matrices, what would this look like? Well, you'd start out with the coefficient matrix 2, 4, 0, 6, 0, 0, 0, 1, 2, 0, 1, 2, 1, 5, 1. If you added the solutions, you'd get something that had 4, 3, I suppose that's a 9. I suppose if that's a 9, I should leave it as a 9. Okay. So then you could do row-reduced echelon form and notice that you'd get to the augmented matrix for this system. That would be 1, 2, 0, 3, 0, 2, 0, 0, 1, 2, 0, 3, 0, 0, 0, 0, 1, 9. Okay. The question is, how do you get the system equations from that matrix set? Well, what I'm looking for here is I'm going to look for columns that look like columns of the identity matrix. And I'm going to say, well, one solution is x equals 2, 0, 3, 0, 9. Why is this? This column corresponds to the x1s, the x3s, and the x5s. How do you see that? Well, if you went over here, that's what this represents, and you crossed off all of those columns that didn't look like identity columns. If those were zeros, if you had 0 x2s and 0 x4s, then what would you have? You'd have the identity matrix. In other words, you'd have just the equation x1 equals 2. You can see how that happens. x3 equals 3. x5 equals 9. That's what I end up with. Slightly more subtle is, how do you get the list of all equations? Well, you'd need things that actually didn't change any of the equations at all. So think about this. If I happened to have an x2, if I had one x2, Well, what would I need to do to keep all three of these equations true? Well, if x2 were 1 larger than it used to be, then this would need to be 2 smaller than it was originally, and the rest of the variables would need to stay unchanged in order to keep this equation true. Okay? So notice that this is actually a solution to the homogeneous system of equations right here. This vector keeps this unchanged. Okay? Similarly, you could say, well, what would happen if you added a extra unit to x4? Well, it turns out that if you had 1 in x4, it wouldn't change your x5s at all. But if you had 1 x4 and you were trying to keep this equation true, you'd need an extra -2 x3s. You wouldn't need any more x2s. And you need an extra -3 x1s. You can see how those numbers could be pulled off from right here. Yes? So here what you're going to look at is you're actually going to look at the height of it in the rows, in the columns. So in this column you can see that the 2 there, we're going to need the negative reciprocal for the x3 variable. We'll need the negative reciprocal here, and because this is in the x2 column, we'll put a 1 in x2 and we'll take the negative reciprocal there. So the solution set would look something like this. Plus a, -2, 1, 0, 0, 0, plus b, -3, 0, -2, 1, 0, where a and b are real numbers. Now, if you were looking for the homogeneous solution set, the one where those didn't exist at all, notice that would be exactly this solution set without that single vector, i.e. the solution set of the homogeneous set of equations would be a two-dimensional vector space, where this is my basis. This is a two-dimensional vector space shifted away from the origin, so it looks like a two-dimensional plane, except for that it's shifted up. Hope that helps.